Everyone, and welcome to The Explainer. Chances are you trigger complex AI algorithms literally hundreds of times before lunch. Whether you're just scrolling through a feed, typing out a quick email, or relying on a map app to get you through traffic. But how often do we actually stop to think about the exact recipe running under the hood of those apps? Well, today we're going to dive deep into the advanced concepts of modeling in AI. We are pulling back the curtain completely to explore the raw ingredients, the mathematical logic, and the specific architectures that let a machine go from basically a blank slate to a highly intelligent decision maker. Let's get into it.
Here is our roadmap for today. First, we'll define AI, ML, and DL. Second, the language of data. Third, rule-based versus learning-based approaches. And finally, Category 4, the different categories of machine learning.
Okay, Section 1. Defining AI, ML, and DL, the big picture.
So, to really get this, think of these fields like Russian nesting dolls. There's this brilliantly nested relationship here. Artificial intelligence, or AI, is the biggest doll. It's the broad umbrella covering any simulation of human intelligence. Historically, that relied heavily on predefined rules that humans had to manually program. Now open that up, and inside you find machine learning, or ML. It's a subset that steps away from strict human programming, instead using algorithms to automatically learn patterns from data with way less intervention from us. And then, right in the center, you have deep learning. This is a highly advanced subcategory of ML powered by complex artificial neural networks. Deep learning completely automates the feature extraction process. It lessens human intervention even more, though it does demand massive amounts of data to pull off complex stuff, like natural language processing or driving a car all by itself.
Moving right along to Section 2, the language of data, AI's building blocks. Before a machine can learn a single thing, we have to feed it information, right? The very first critical building block is what we call features. Think of features as the columns in a giant spreadsheet. They represent the specific, measurable traits the machine uses to actually understand an object. So if we're trying to teach a machine to identify fruit, the features might be the exact RGB color values, the weight in grams, or even the mathematical curvature of a banana.
But here's the thing. Raw measurements just aren't enough on their own. While features describe the object, we need labels to tell us what the object actually is. Labels are essentially special features that act as a definitive answer key. They attach meaning to the raw data. Going back to our fruit example, if the features map out something that is red, round, and weighs 150 grams, the label we attach to it is simply apple. When data has these tags securely attached, it becomes what we call labeled data. Next up, we take all those features and labels, and we compile them into training data. Think of training data exactly like a teacher handing out thousands of examples and illustrations to a classroom to teach a really complex topic. We give the AI model this massive collection of labeled examples so it can sit there, study them, compute all the statistical patterns, and really learn the relationship between any given set of features and its correct label.
Once the machine has fully processed that training data, we've got to verify that it actually learns something. And this is where testing data comes in. To keep our classroom analogy going, testing data is the final exam. Crucially, though, this test is given without the labels, no answer key. We just present the features, ask the machine to make a prediction, and then we verify its answers against those hidden labels to see how accurate it really is. This is the absolute final hurdle before any AI system is trusted to operate out in the real world.
All right, Section 3, rule-based versus learning-based, two paths of modeling.
We have seen a massive paradigm shift in AI modeling over the last decade or so. In the old-school, traditional, rule-based approach, a human developer takes the raw data, explicitly writes out the rules, like, hey, if a customer asks about shipping, give them this specific tracking link, and then feeds both of those into the computer to get the answers. But with the machine learning approach, that entire flow is fundamentally reversed. We feed the computer the data and the answers, those labels we just talked about. The machine takes them, does all the heavy mathematical lifting, and outputs the rules all by itself. It's wild.
Now, I'm sure we've all been trapped in a frustrating loop with some customer service chatbot that just completely fails to understand your unique problem. Well, that is a prime example of a rule-based system failing in real time. Because the developer hard-coded the instructions, the system's learning is entirely static. The machine does exactly what it was taught once, and literally nothing more. It can't adopt to new data, and it completely fails to improvise when you give it feedback.
Which brings us to a huge roadblock in software development. In the real world, information is never static, right? New trends pop up, environments shift, user behavior has evolved daily. So if a rule-based model can't adapt, What happens when the data inevitably changes? The answer, and honestly the eureka moment in modern computer science, is the learning-based approach. This is the dynamic solution where we basically abandon the impossible task of programming every single possible scenario. Instead, we architect the computer to learn how to do things by analyzing examples or processing feedback, much like how we learn from our own experiences. Because the system is calculating the rules independently, it can seamlessly adapt to shifting data without an engineer ever needing to rewrite the underlying code. Let's move into our final section, Part 4, Categories of Machine Learning, the Learning Recipes.
The learning-based approach is pretty broad, but we can generally divide machine learning into three main paths: supervised learning, unsupervised learning, and in reinforcement learning. Let's break down how each of these uniquely tackles the job of extracting knowledge from data.
First up, let's compare supervised and unsupervised learning. The defining difference here is all about the labels. Supervised learning needs a human to provide nice, clean, labeled data. We use it when we want the machine to learn a specific relationship to predict future trends, like guessing the price of a house based on past sales in the neighborhood. Unsupervised learning, on the other hand, deals with messy, unlabeled data, no tags whatsoever. Instead, we unleash the algorithm to hunt down hidden patterns entirely on its own. This is incredibly useful for stuff like dynamic customer segmentation or flagging weird, anomalous transactions to stop credit card fraud.
Now, within supervised learning, we actually have two primary models. The first is classification. We use classification when our data falls into distinct, separate categories. Imagine an AI optical scanner sitting above a factory conveyor belt. It learns the features from its labeled training data so it can accurately classify new items as they zoom by, essentially drawing this complex mathematical boundary to separate the apples from the strawberries in real time.
The second type of supervised learning is regression. So, unlike classification, which dumps data into discrete buckets, regression maps out continuous data. It looks at historical labeled data points and draws a predictive trend line to forecast a continuous numerical value. Think estimating exactly how much the temperature will drop tomorrow, or predicting subtle shifts in a company's stock market valuation.
Okay, now let's look at a completely different paradigm altogether, reinforcement learning. I find this one absolutely fascinating because there is no initial labeled training data to study at all. Instead, the machine learns purely through an environmental reward and penalty mechanism. It's basically a high-speed game of trial and error, where an AI agent makes decisions trying to maximize a reward metric without ever being told how to actually win the game.
Let's walk through how this looks. Imagine our AI is trying to identify fruit again. First, you showed an image of an apple. The machine has no prior training, so it just takes a wild guess and predicts cherry. You then give it negative feedback, a mathematical penalty. The machine updates its internal logic, basically noting, okay, those specific features do not get me a reward. The next time it sees those features, it predicts apple. Boom! You give it positive feedback, a reward. And through millions of these rapid-fire trial and error iterations, the model hones its accuracy to near perfection. Finally, we reach the apex of all this, deep learning. When we scale these learning processes way up and start using artificial neural networks, which are structurally inspired by the human brain, by the way, we enter a seriously advanced domain. By feeding these multi-layered neural networks massive datasets, the software can actually train itself. Crucially, it automates the extraction of its own features. This allows the system to perform incredibly complex, almost human-like tasks, like analyzing the raw pixels of a photo to confidently identify a specific species of bird in mid-flight. It's just incredible.
We have covered a vast technical landscape today, from the basic definitions of features and labels to the dynamic, self-improving worlds of unsupervised and reinforcement learning. The leap from static, rule-based software to highly advanced models that learn and adapt from their own experiences is profound.